Tigadan 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 pam pam tigadan 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 pam pam tigadan 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 pam pam tigadan tigadan pam pam tigadan tigadan.
Up next is Ravi Cheema from the National Energy Research Scientific Computing Center, where he works within the storage group within NERSC. Ravi, how are you today?
Hi, hey guys, this is Ravi. Can you guys hear me?
Yes.
All right, cool. So let me start by first sharing my screen. And, all right, so this is Ravi Cheema. I work for National Energy Research Center, and I work in their a storage team that manages the off-compute storage or storage, which is long-term storage mostly. So let's today I will be talking about the like a few slides of NERSC systems overview, and mostly talking about our new file system, which is called Community File System, and how we got there and what we did to get there. So something about NERSC. NERSC is a very diverse community. We have like lots of users, around 8,000 users, 900 projects, and lots of applications. And we have a lot of different kind of applications. Each user has their own applications, and our systems are not aimed towards just running a single application, but lots and lots of different applications, different kind of data, small files, big files, and all kind of stuff. Yeah. So in storage, in the computes, we have a Scratch, which keeps, which is just large enough to keep a couple of weeks to maybe a month worth of data, and after that it gets purged. And after that, the next tier is community storage, which is more hosts users projects, and this is kind of semi-long-term storage where they can keep their their files for years, you know, maybe not decades, but years. Yeah, and this storage is mounted on computes and our Kubernetes clusters and our DTNs. And also the science gateways. So the next tier is the archive tier, which is the tape tier, and it's HPSS based. It's not mounted anywhere, but it's accessible using HPSS tools from anywhere, so that users can just put their files in there and access it. And this is supposed to be for decades old data. You know, it's not supposed to ever be purged. So here's the overview of NERSC as of today. As you guys know, that we are currently in process of building our next computer, which is called Perlmutter. And I will not go into details here, but I just want to point out that this diagram shows two different networks. One is our Ethernet network, which is currently 100 gig. Connected to the clients, and the second network is the FDR InfiniBand, which is kind of old fabric that our current storage uses, connecting to our current compute, Corey, and also to the data transfer and other resources. Whereas in one of the future talks, we'll talk more details about the networks for Perlmutter, but we are just not there yet today. So here's a brief overview of Perlmutter. Perlmutter is a Shasta system from HPE. And right now we are in the middle of implementing it's a phase one, which has GPU nodes, around 1,500 plus GPU nodes, and some non-compute nodes, which includes service nodes and login nodes. And we haven't decided how many of them will be logins and how many will be service nodes. And then this phase two is brings CPU computes, about 3,000 plus CPU nodes, and which are all AMD based, and also has a bunch of large memory nodes in there. And our network for within the Perlmutter is called Slingshot, which is Ethernet based. And it will also have its own Scratch file system, which is 35 petabyte of all flash Lustre file system. So Perlmutter is basically it's optimized for running different kind of jobs. It's like all our NERSC systems. We are not designed to run a specific kind of job because our users come from all over different locations. And it will have both GPU accelerated systems and CPU only systems as well, and a few really large memory nodes. Very fast Scratch. But as you guys know that I mentioned in the previous slide, our Scratch is only 35 petabytes, which is not as big as our core file system. All right, so the next slide. Now I will talk about our community file system, which is supposed to be the next tier after the Scratch file system. This is where the users will store their files in their project directories, and we call it community file system. So we started implementing community file system in 2020, and this all started more than several years before 2020 when we started planning for it. But in 2020 is the one when we first saw the file system, and our file system is. It's basically a capacity tier, even though it has InfiniBand connections. We weren't aiming to get any much high throughput from it because that's what we don't want users to run their compute jobs off from it. And it's initially started with a 60 petabyte in January, and now we are working to get another 60 petabytes, so it will be 120 petabytes in next few months. And it's supposed to be a user-centric file system where they can store all sort of files, different size files, small, large, and also have snapshots if they need to revert back to any previous version of a file. And we enforce all the quotas on users, even though the quotas are pretty big for users. It could get almost up to a petabyte per project or at some places. So the storage group needed some durability because this is a huge file system. We wanted it to be operationally sound. That means it continues to run without causing problems. And we also wanted to have a good monitoring for it so that we know how much data is getting pushed into it, how much data is coming out, and also to help us with ongoing maintenances like the upgrades, the firmware upgrades, software upgrades, and also it should be able to accommodate the files of our users from little bitty files to terabyte size files. So we went through, before 2020, we went through a lot of different technologies and finally narrowed down to IBM's ESS solution, which runs a spectrum scale, and back in the days it used to be called GPFS. So each, like I mentioned that we have 7 ESS storage units in this file system, and each storage unit is like pretty dense. It's packed with 11 petabytes of space in one rack. So we call one rack as one storage unit. So each rack has 2 I/O nodes, as mentioned in the diagram on the left here, and it has 8 enclosures. Each enclosure has 106 14 terabyte disks in there, and they're connected to the both I/O nodes. The I/O nodes run Spectrum Scale's ESS code that does, the RAID and the like V disks and everything, and it manages all those disks. So we also have a test system, which is just to test the firmware upgrades and other problems that we might run it, which is pretty small. It's only a 2-node system with 2 enclosures with 10 terabyte disks. Like I mentioned in one of the previous slides, the system was implemented in 2020, around January 2020, and our previous file system, which was called Project, was also based on GPFS, and it was around 6 petabytes of data, around 1 billion files. And for those of you who are familiar with GPFS, it has file sets, and which is basically isolating the data kind of thing. So we had 1,500 dependent file sets on the project file system. So our challenge was how to get all that data onto the new file system. And like I mentioned, our users are pretty diverse, and we did not have a standard directory layout because each user had his own workload. So all the files were kind of all over the place, small, large files, sparse files, some files sitting there for years, and some are getting churned like on daily basis. So it was all over the place. And on top of that, some of the users, I'm not sure if they do it intentionally or programmatically, means the file names and directory names have all kind of extra characters that you will not type in, or you have to do some kind of escaping of the characters if you parse them through a script. So that was another challenge. So we talked about lots of different options. What can we do with the new file system? First was like, we just stand up a new file system. There's nothing on it. We just tell users, here's a new file system, go copy your own files on it. And we'll let you know that in 6 months, we're shutting down your old file system. So you're on your own. So we thought about that. Then we also talked about using Spectrum Scale or GPFS's AFM solution. It is kind of a caching solution that GPFS has, and it can be used for migration. So we tried to test that. And then we also thought about why create a new file system and but add the new disks into the same old file system, just increase it and run a GPFS restripe. And then we started looking at tools. What if we have to do the migration? We went into testing mode here and started looking at the MPI file utils to see any kind of parallel copy, experimental scripts out there, And we also tested the traditional tools like rsync and tar, which are like time tested, and we've been using it for decades. And those are the ones we ended up using because we kind of trusted those. So let's talk about the first option that we discussed, was to have users migrate their own data, which was pretty risky. Means you tell a user to migrate their own data. So on our file system, we had projects, not users. So each project could have like tens of users in there, and each subdirectory could be owned by a different user. So there's not a clear owner of the data in a project directory who could just migrate all of it. So we had to just shepherd like 50 plus users in a project directory to migrate their own data, so which was kind of troublesome. And then each user also collaborates with lots of other users in this scientific research, and that means some of the files could be owned by different users, even in their own data. So they could run into challenges where they say, oh, I could not access this file, could you copy it for me, those kind of scenarios. So it was going to turn out to be pretty messy. We ruled that out. So next option, we started a test bed and started testing GPFS AFM to migrate the files. But back then, I know quite a few of these are already fixed, but back then we ran into the problem because we had 1,500 independent file sets on the file system, and AFM did not support dependent file sets, and it supported independent file sets, which is a completely different thing than dependent. And we did not want it to use those independent file set. So that was first a red flag. And then there were other things that we run into. They were like we could not maintain the timestamp on the directories, that were getting copied. The files were okay, but directory level timestamp was a problem. So, but we contacted IBM. They talked to us, and they showed us the roadmap that they were going to fix these, but that roadmap did not meet our timeline. So we had to somehow get all the data to the new file system. So AFM was not something that we wanted to use. So the next option was to get all this new storage of 60 petabytes and add it to the same storage that we had in project, which was 6 petabytes of data, and then just expand the file system, and which is pretty easy, which is a time-tested technique in GPFS that you add new storage and you can remove the old hardware underneath the file system. And users might notice a small slowdowns when we're doing this, but they will not notice any outages, which is pretty good. But that also meant that we had to keep the same old file system, that we could not change its block size. And we had 4 megabytes block size, and we wanted to use the 16 megabyte block size. And in the 16 megabyte block size, and with the new file system versions, there were new features in there that we wanted to use, because our file system is so diverse. It has small files to really large terabyte size files. So we wanted to use a feature called subblocks, which more efficiently stores both small files and the large files. So we kind of decided not to use this either, because we were like, okay, in future, our file systems will only get bigger, and at that point, it will be much harder to migrate the data onto a newer version. So let's just move forward and start migrating the data using the tools that we've been using for years, using rsync, tar, just a parallel command to parallelize these, the basic commands of copy, rsync, fpart, and tar. So what was the plan? So to migrate 6 petabytes of data, what we did was we, GPFS or Spectrum Scale has an ILM engine, information lifecycle management engine, that lets you quickly, run policy-based jobs to do things to the data. So we used those tools to generate a nightly file list from the file system, like 1 billion files. And then we wrote some scripts and divided those files into smaller chunks based on the per project, and then even further down and then we used the fpart command to break down each file list to like 10,000 files per list. And then we stood up a client cluster of 16 nodes. And client cluster, it's just GPFS clients, and we just want to use this CPU. And we started running the tar parallelly on those files for the initial copy, and we didn't use anything fancy, just a parallel command to parallel those tar commands. And when the tar was completed, our next step was to run rsync to catch up on any changes that have been made since then, or also copy the things that we might have missed in tar, like ACLs or extended attributes, or anything that users might have put on the files. So we basically tried to do this over the Christmas break. That's when our user base is mostly running less jobs, and then we also have a data center, holidays, even though we are running, but it's pretty minimal. So the step one was to take the snapshot of a file system, the project file system, which is our old file system. and then run the tar from that snapshot. And then when the tar is completed, we will have a new snapshot to run the rsync on the per project directory based. And we have only 2 servers to do the rsync because the rest of the servers were just dedicated to do the first copy of the data using tar. So we had nightly report to see how many files are getting created every night, and it wasn't a lot, but just to make sure that we didn't miss anything, we also started running rsync in dry run mode to see how many files were changing. We just wanted to have as many checks as we could to make sure that we don't miss anything, because once the old file system is gone and a user comes back to us, he didn't get his files, it will be very hard to get those files back. So it was basically 2 people operation. Ray was one of our engineers. He retired right after he was done with the migration. He said, I don't want to do this again, ever. And the second person was myself. So Ray first took on the rsync part. He said, Ravi, you do the initial copy. As soon as you're done with one project directory, you hand it off to me, and I will run the dry runs with rsync and do the more rsyncs using the file list that he was generating from dry run. It was going to be faster that way. And, so it was a tag team. So we worked like that for almost 2 weeks, for initial copy. As soon as the smaller project directories were copied, Ray would run rsyncs, and after rsync was completed, he will run multiple rsyncs, like nightly rsyncs after the new snapshot was created every night. So in the end, when all the data was migrated, and we were just down to running nightly rsyncs, it was taking us every 2 days to catch up for the changes. So which was pretty good. We were like, okay, cool. So we just have to tell users that we'll be down for 2 days and we'll just run a final rsync, and we'll be done with it. But as we moved closer to the deadline, and our window, our rsync window kept improving, and now we were down to 12 hours or under 12 hours. And maybe one of the reasons for this could be, we're just speculating here, is that because it was holiday season and there were less users doing work, and we were also getting ready to shut down our systems for the holidays. So yeah, that helped during the migration. So the next step was the final rsync. That's when we shut down all our systems during a maintenance window, mounted project file system, which is our older file system, as read-only, and the new file system was not available to the users at the moment. And then we brought up the systems, handed over to the users, told them that you have access to the old file system and as read-only while we work on your migration. And we started using all the 16 servers that we had in a test temporary client cluster to run rsync parallel. All the file system, not file systems, all the file sets, which are equivalent to the project directories. And we were able to complete it in less than 12 hours. And even after we could spare time to run a few checks. Like I mentioned, Ray used to love running check everything after rsync using dry run to make sure that we didn't miss anything. And we also ran another rsync with checksums enabled, which was not an option earlier because amount of time it would take to run checksums on the files. So we completed that for like 90% of maybe 99%, and we had to stop that because we were running out of the maintenance window. So going back to the process that we went through, we thought about what could have we done differently. So we were a little tight on the testing window. we could have explored other tools than rsync, but we did not want to use a tool that we have not tested or tried ourselves in the past and we did not trust. So there were lots of good tools out there that say that they could do parallel copies. They could tie into the spectrum scale ILM to generate the policies, the file list on their own. But we did not have our hands on those. And so we okay, we don't trust that process yet. So we just created our own process. We put all the things together, the ILM scans, the ATARs, the rsync, the parallel command, and everything to migrate the data on our own. So in rsync, the dry run was one of our good friends. The reason I say is because we would run dry run between a snapshot and our new file system. Well, the snapshot's on the old file system, and it will give us a list of files that it need to update. So all we had to do was just update those files instead of running a complete new rsync. So which was pretty handy in keeping the new file system in sync with the old file system before the maintenance. So, and also we used ILM scan to get the list of files, and we broke it down to 10,000 files per job, per parallel job. So we did that on 10,000 on purpose because we thought, what if one of our client node crashes, it runs out of memory. So all we lose is one job, which is 10,000 files. All we have to do is rerun that job again and copy those 10,000 files again. So it's just not as bad as copying a billion files again. So which kind of helped. We ran a few nodes out of memory, and we had a couple crashes. So, but we did not lose much time in that. So I wish the next one is I wish we had enough time to run checksum on all the files, but we did get to 99% of files using rsync checksum, and I wish we had more time. But we like I mentioned, Ray, he's always belts and suspenders. We'll always want to check more again and again and again after we copied the data, and after we announced to the users that everything was copied, and he didn't give up. He just continued to run checks on the files, try to compare if our process missed something, or if he missed something, if I missed any files. So the migration rates were pretty good, and it depended from time to time, because if we hit a directory with smaller files, it took longer, and if it was a couple of large terabyte size files, it went pretty fast. So it ranged between 5 gigabyte per second to 32 gigabyte per second of aggregate across all the nodes. So the bottleneck was our older file system here, the project, because our newer file system was built to support 100 gigabyte per second transfers from the day one. So the conclusion is that there's no easy way out of a data migration. If you could talk to vendors, you could pay them hundreds of thousands of dollars to use their products that they have created to do data migration, or you can put something together on your own. But the bottom line is that it's really, really a lot of hard work, and everybody needs to triple check their work, because this is data that, some of the data was generated years ago that users might not be able to create it again. So it was very important. So in the end, the process was it was a handheld. We were always watching 24 hours a day, So, but the most important thing was that the users did not have to migrate their own data, which was good. So, and we successfully migrated the file system, and we ended up using a new file system instead of growing an old one, so we could leverage the new features that came with the new file system, and there was almost a very small amount of downtime. We announced 5 days of downtime, but we ended up with only 12 hours, so which was not bad. And like I mentioned, my coworker Ray was really checking everything. So after the migration, he did find that we missed a few things. Both tar and rsync did not work well with the hard links. So a lot of hard links, they were created as new files in our new file system, but none of our users found it or reported it, and we found it on our own, and we went back and fixed those hard links. So a lot of users they did not even know that they were on the new file systems, other than that all of a sudden they got a huge new bigger quotas. Because we mounted the new file system as a new mount point, we created a symlink to the older location, so the users can seamlessly, when they come back to the system, their same scripts and their jobs will continue to run. Of course, over time, they probably figured out that they're just using a symlink, not a real file system, and the new file system is called something else, not project. But yeah. Okay, so now that we have a much bigger file system, means our previous file system was only 6 petabytes. Now we are looking at something that will be more than 100 petabyte file system. So it brings its own different challenges. We have almost daily hardware issues that in the past we would think such a big deal. Now we are like, okay, fine, another disk failed today. So, there's a constant churn of disks. There are always slow disks in the file system that could slow down the users. So we picked IBM solution for, lots of its features. And one of the things that we really liked is that even a single slow disk in a system could slow down everything else. So, they have features built into it that could help removing the disks that are not working up to the standard. So that meant a lot more disk failures. And we've been, now we have a pretty smooth procedure that, disk fails, our operations people pick it up, contact the vendor, and vendor, in this case, IBM, their people come on site and replace the disks. So, which is pretty streamlined now. And the next big challenge that we have with such a big file system is firmware and OS updates. The IO nodes are based on Red Hat Linux, and there's a whole sort of firmware from the enclosures, disks, the HCAs, the IO servers itself. I know every vendor out there you talk to, they always say, "Oh, we support rolling updates. You will never go down." But I've worked in the storage industry for a very long time, and I never trusted that statement. So there's always a hiccup, if not a downtime, when you're doing the rolling upgrades. So users can notice the slowdown. When you are taking one IO node down and you think the other one is taking care of all the IO, but the users who's running a really big job, he say, "Oh, for a minute or so, something happened there. What was it?" So it's never seamless. So we try to do it in the maintenance window, even though it's a rolling upgrade. So another impact is with such a big file system, we had to think about scenarios where it could go down. It could go down for multiple hardware failures, or it could go down for, we've seen this in the past, the data corruption that happens everywhere, So, and our file system is connected to our compute nodes, spin nodes. Spin is a Kubernetes nodes, our web portals, and our GPU nodes. And, we had to somehow, see how how to minimize the impact, but we could not find a work around it. Means if it goes down, which it hasn't, but we have so much redundancy built into it, we don't expect it to go down, but there's a chance that what if it goes down, we have a power loss in that row in the data center or something, So, and the other thing I talked about, the file corruption, and if we have a file corruption, we end up running FSCK. It could go for days and days. We thought about the scenario, but it's something that we are also working with the vendor to see if they can move some of those requirements for online checks instead of offline. So there's something there in future, but not quite here yet. Other thing was the data management. The large quotas means a lot of files, and but we are leveraging IBM's or Spectrum Scale's ILM scans to gather nightly inode scan of all the file listings, so we can provide it to the users who wanted to look at their files. It's there. So if we don't want users to running find commands or or those kind of things to look for their files on the file system. We would like them to just sort through this one file that we provide them every night out of a snapshot. So so we can make the file system working at a reasonable speed for all the users. So it's a mixed use file system. Like I said, we have a variety of users, small files, large files, some even use it for, they don't tell us, but they use it for the computations on the computer systems. So, this file system is mounted as read write on the computes as well. So those are challenges, ongoing challenges we have to deal with. And something we haven't thought about that is what will we do after this file system is ready to retire in 5 to 7 years? At that point, its size will be more than 120 petabytes, and how will we migrate at that point? Means this presentation is migrating about 6 petabytes only, which looks pretty small now, but back then we were migrating, it was a huge number. So we haven't thought about that, but maybe, 5 years down the road, I'll have another presentation like this. So what are we doing now? So we started with a 60 petabyte file system in 2020. Right now, we are in the middle of doubling that file system to 120 petabytes. So we are upgrading, we are adding an upgraded version of ESS, which is called E5000 to the data center. And right now, as we talk, we are adding that storage to the file system. And then we will remove the old storage. Now we call the old storage is the one that we talked in the last slide, is the ESS, because that ESS is based on Power 8 systems, and we will be going through upgrade to get them to Power 9 systems in next couple of months, and then adding it back in there. So how did the new implementation go? We are all in the middle of pandemic, and we had the timelines to implement the next phase of 60 petabytes during the pandemic. We didn't choose it, but it just happened, like to everybody else. So we had instructions to do social distancing. We could not work with each other like a team, work with each other as a team, like a physically present in the data center or in an office. But the file system shows up on the loading dock. You have we had to work with the people who could help us instead of us going on site for work to get it unloaded. And then a vendor had to send their people and work at socially distanced, maintaining all the COVID protocol to rack all our equipment, get it built up, and there was a power upgrade. We had to move everything to the 60 amps on all the racks. So a lot of electrical work, but everything, our great team at NERSC and with help from IBM, they managed to do this during the pandemic lockdown. So that was implemented, and finally we are at a point right now where, like I mentioned earlier, we are adding that new storage, and we are almost like only a couple of months away from bringing our 60 terabyte file system and turning it into 120 petabyte file system. And here's a layout of our new ESS, which is a little bit different. In the previous ESS, our IO nodes were right in the middle of the rack. In the new ESS, they are on the top of the rack, which we don't mind. Our vendor IBM said this is for the better management of the cables, so which is good. You know, cable management is always good. So yeah. So here's the difference between why we are upgrading our old system, old ESS to Power 9, because it has better CPUs. It provides us IBM Mellanox ConnectX 5 HCAs, and it has more memories. It's use a NVMe disk instead of SSD for log tips, which log tip is an internal feature in ESS to storage rollback logs. And Power 9 is based on a PCI Gen 4, and it runs Red Hat 8 based operating system. So it provides us a little bit of a performance boost if you move to Power 9. So that was the main driving reason behind this. So what's left ahead of us, like I mentioned, you know, we are in the middle of data migrating from old ESS to the new ESS, and the next steps are just shutting down the old ESS, doing a hardware refresh of the servers, move them from Power 8s to Power 9s, and then bring them up, you know, and then integrate into the file system, and finally have 120 petabytes of file system. So here's a picture of all the steps, what we have been through over the years. You know, the phase one was the very first block on the left, where we implemented 7 racks. Then we phase 2, and we kind of named it 2.5. Right now we are at where we are merging to, you know, the circle part. We are merging 2 file systems. The next step will be the breaking them apart again and upgrading, then merging them back again. So here's the NERSC team. As you can see, you know, you probably know Christy Callback Rose, but she's our acting group lead, and we would like to keep her as a group lead. But there's always a opportunity for other people to apply. So we have an opening for the group lead for the storage group. If somebody's looking for relocating to the Bay Area, or you know, or a challenge, please feel free to apply. And I think that was my last slide. And if anybody has questions, let me know.
Thank you, Ravi. Yes, we do have one question. Well, we had 2, but you'd already answered it in your presentation regarding the file system. But in terms of backing up, will you be doing backups of the new 120 petabyte file systems, and how do you go about doing it?
Yeah, so we gave up on the backups a while back. Means at that scale, we just can't back it up. So like I mentioned, we have a archive a tier, which is HPSS, and we rely on users to do the backups to the HPSS. So if a user does not have backups on HPSS, we do not maintain any off-system backups. But on-system, we have snapshots. So as you know, the snapshots are still on the same disks. So it's not really a backup. It's just a version rollback for users. So if a user deleted his file yesterday, and he found out today that he deleted his file yesterday, he could go back and get it from the snapshots. So that's the only thing that we offer.
I have one question, fast one, Ravi, if you allow me, Brian. It has to do with the Spectrum Scale container storage interface. Do you have any, did you work with it? Did you have any experience with it?
Yeah, so we explored CSI, and we have right now we have a Kubernetes cluster, which users run their own containers in there. So we experimented it, but we did not think that we needed it because CSI provides a lot more features than what our users used. Our users just needed access to the file system, just like a regular file system. So which is done by just having loopback mounts on the within the Kubernetes containers. But with CSI, what we experimented was it lets you run, launch a container and then talk to the file system cluster through its API and create a file set or a directory on the fly, and then also clean up afterwards too, which is more like I would think a Scratch kind of workload where you're launching a job and after that you want to clean up. And we really did not find a use for that at the moment. But in future, I didn't talk much about our perimeter computes, because it's not ready yet. But it's based on containers. So it's a possibility that in future we might revisit it. But at the moment, we are not using it.
Thank you.
All right. Thank you, Ravi.
Right. Thank you.
Bum 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 bum.